in today's lesson, we will learn about the second method in the segmentation, which is based on the edge detection. So the first method that you have learned is in terms of the thresholding, in which you have the global method based on the also method, or the local method, which is based on the adaptive method, which relies on the mean C in order to determine the output as seen in this image. So today we will learn the second concept, which is based on the age-based segmentation, in which, as you can see from the outcome of the segmented image, age means that you find any boundary in the image, which is relies on the discontinuity of the image gradient. So as you can see from this cap of the image, so there is transition of the gradient of the image, so it will generate the outcome in which the age for this particular image. So basically, why we use the age-based segmentation? So this is based on the simple concept on how you will use the red blood cell image. So basically, from the blood smear image, which is the RGB, if you use the simple thresholding method, global thresholding method, you will have this binary image. So for this binary image, you will see there is a lot of the cell. So most of the cell condition is clump or overlapping between each other. So the problem is that we want to count how many cells there is appear in this image. So if the cell is not touched between each other, it's quite easy to estimate that thing. But since the cell was touched each other, so the next step is that we convert the image to the age representation by using the Kane edge detectors, and then based on the generated image here, so we can estimate how many circle that can be constructed for each of the generated edge. Then from based on the number of circle, we can say this area belongs to 4 circles. This is 2 circles, and then etc. If we continue the whole process, we can actually estimate how many circles that is corresponding to the red blood cell that appear in this image. So that's one of the implementation of the age that you will determine from the segmented binary image. So for the age-based segmentation, as I mentioned previously, it will relies on the discontinuity in the image data to locate the boundary. So for instance, for this image, if I construct a simple window here, so this window will be represented as an edge in the right area. So why the edge appear here is because of we have some discontinuity of the pixels gradient inside of the constructed window area. So for the edge-based segmentation, basically it can be divided into two important steps. So the first step is to find the edge, or the we call that thing as the edges. Edges means that is the pixel point that is belong to the edge. So you need to remember that the edge means that just a single pixel point that was generated based on the image. So the second step is edge linking. So as can be seen in the illustration, edge linking means that you have constructed the edge. So edge linking means that how you're able to make sure or ensure that all the edges will be connected between each other so that you can construct either line, either curve, or etc. So for the edge linking, there are two methods. The first one is based on the local processing, which relies on the magnitude and direction of the gradient. So the second method is based on the global method, which is known as the Hough transform. So we will learn about these two methods, how we can utilize the method in order to link between the edges. So for this class, for the edge detection, we will use two type of operator. First order derivative, which is based on the gradient operators, and then the second order derivative, which is based on the Laplacian operators. So both operators was actually constructed in a digital form in which it will be represented as a kernel, or we call that thing as the window size that will be flat throughout the image. The same process with the min minus c operation. So we will talk about their properties, how we can use the first order and second order derivative properties to determine or locate the agile location inside of the image. So first thing first is that about the properties for the image itself. So in general, if you have the binary image, you have the grayscale image in this representation in which you have very distinct transition from the black to the gray area. So in this case, you can actually generate very good profiles of this particular image. So this is the profile of the gradient transition between these two areas. So, however, mostly in the normal image, your transition is not very distinct, in which it will consist of some slope or some small transition between image from blacks to the grayscale area. So this transition area will actually generate what we call as the RAM profile. So RAM profile, in contrast with the binary profile. So for this binary profile, which is quite distinct, you can actually locate the edge simply by pointing out this area. However, for the RAM profile, since you have the transition in the RAM, so your edge will be generated based on this particular area. So in general, you will generate quite thick edge from the image. So this happened because of many reasons. So one of thing based on the optics, sampling, or image acquisition perfection. So for the thick image, the slope of the RAM will be inversely proportional to the degree of blurring in the image. So the meaning of this sentence means that, so if the slope of the RAM is very steep, so means that you will have very thin edge. However, if the slope of the RAM is very flat, so for this case, you will generate very thick edge. So if for this RAM profile, so it's quite impossible for you to determine the thin edge directly. So we need to do some processing in order to determine that thing. I will show you later on. So for the thickness of the edge will be determined by the length of the RAM. So this is the same explanation as in here. As been mentioned previously, we have two types of operators to generate the edge. That is based on the first and the second order derivative. So basically, based on this image, in which we have the rim profile of the image. So for the first derivative, we can simply find the edge in which it will be based on the profile of the RAM. As for the derivative, second derivative will generate two distinct points in which from the different direction, point out or point down. So in which this will be known as the transition of the gradient profile in the image. So it can be in the reverse direction, which is the point down first before the point up, or vice versa, has been seen from here. So basically, from the first derivative, one of the bottleneck is that the type of the edge that will be generated, it will be very thick, which is directly proportional to the RAM profile for the image. However, for the second derivative, we have to distinct point of the transition in which this information can be utilized later on in order to generate a quite thin edge for the image. So for the second derivative, we have two transition point in which the point up and point down that will be denoted as the positive or the negative direction of the edge. So from these 2 points, we can actually generate what we call as the zero crossing. Zero crossing means that you generate the line from the you generate the line straight away from the peak of the two transition point, and then as this line cross the zero axis, so this is will be known as the zero crossing. So zero crossing will be quite useful in order to determine the center of the edge in which you will have very thin edge later on. So in this slide, I will show you what is the effect of the noise as a result of the derivation operation. So basically, for this image, the first column is the gradable profile of the image, and then which its corresponding noise was generated from the Gaussian noise. The second part is actually the first derivative outcome, and then the third column is the second derivative outcome. First derivative, second derivative. So in a simple way, this is the RAM profile of the image, first derivative, and then the second derivative. So let me clear up the screen first. So for the So the next part is that if we increase the amount of noise, let's say in this case 0.1, so you can see there is no significant difference in terms of the RAM profile. So however, for the first derivative, you have very cluttered generated profile. And then for the second order, it will be it's quite worse in comparison with the first derivative. So if we increase more in terms of the noise level, so in this case, first derivative for the first derivative also is quite hard for you to determine the distinct point of the edge. For the second derivative is much more worse, in which you cannot find any point that will be utilized as the edge. So if you increase the noise more further, so this is the resultant image in which you can see it's quite impossible for you to determine the edge for the first derivative or for the second derivative. So one thing that we should note based on this example is that little noise can have such significant impact to the outcome of the derivative operator, either the first order or the second order. So you can see from this particular image. So the rule of thumb is that you should consider to smoothing your image, means that you give some other pre-processing to the image before you generate the edge in order to determine the distinct point if the edge is contaminated with the noise. We will learn about the gradient operator, which is based on the first derivative and then second derivative, and how it can be implemented in order to determine edge. So basically for the first derivative, it will be implemented using the magnitude of the gradient. So how we're able to utilize this thing is first you calculate the x properties of the gradient. So next you find the y property of the gradients, and then later on you determine the amount of the both gradient by using a simple addition, in which you can use either gx squared plus gy squared square root of this thing, which is the magnitude of both, or you can approximate the thing by using simple absolute. operation. So the previous form, which is for the gradient, is based on the continuous form of the derivative. So how we're able to utilize the derivative in the image? So we use what we call as the kernel. Kernel in a simple way is the small window in the odd dimension that will be slide out through this image. So for this case, we have three types of kernel. The first one is the robot, which is the dimension will be 2 times 2. Second one is the Sobel operator, in which the dimension is 3 by 3. And then the final one is the Prewitt, which is the in the same dimension of the 3 by 3. So if you can see from this kernel, let's say for the Sobel kernel, so in the middle of the kernel, the amount of value will be 0. And then for the top and bottom, top will be negative value and then bottom will be positive value. So one thing that you should note, the sum of everything here should be equal to 0. So for this case, in a simple way, it is a matter of from the center point you find any difference between between top and bottom. So means that in the condition where you put this thing in the flat image in which the gradient information will be the same, the outcome will be 0. So in a situation, let's say you put some image in which you have the quite transition gradient between this image. So for this case, all the value here will be deducted will be with respect to the value here. So it will generate in total of, let's say in this case, negative 4 minus 0 in this area. So this value will be later on in order to determine the age. So if you look at from if you look at from this kernel, so means for the Sobel, so this type of kernel will be utilized in order to determine the magnitude in the x direction, whereas in the right side, this kernel will be used in order to determine the magnitude in the y direction. So the same thing with the Prewitt. So Sobel and Prewitt means that Prewitt you just use you don't use any weight value in between of the kernel, whereas the Sobel, you emphasis on the center weight. You increase the weight in the center area so that you emphasis on the center area in order to determine the age. For the robot, because of the arrangement of the kernel, something like this. So this type of kernel will be utilized in order to determine the age of the gradient, which is something like this. So this thing will determine line in the x direction. This is y direction. So the same thing with this part. So this is another example of the mass. So the same thing for this Prewitt. So this type of kernel will be utilized in order to determine age with an angle. So the same thing with the Sobel. So in which area that you put zeros, the design of this thing is based on your requirement. So it means that either you want to find the vertical line, the horizontal line, or the line in respect to the different type of angle. You just need to redesign the kernel in a different arrangement so that you're able to fulfill your task purpose. So this is some simple example how we are able to use the define kernel function in order to generate the proper age. So for instance, you have this type of image in grayscale. So you define the kernel. So in this case, gx will be equal to this type of operator. So what we do next is that we just need to slide this kernel, short image, and then we have the magnitude in terms of the gx direction from this image. So you can see from here, so in most of the area, it will be become black, Only in the transition point of the gradient, you will have some value in which there is what we call as the edge in the x direction. So the next part, we generate the second type of the kernel, which is we emphasis on the area or edge in the y direction. So we repeat the same process, which we slide throughout the image. And finally, we have this GY image. With this thing is the output response with respect to the y direction. This is the output response with respect to the x direction. So finally, we find the total magnitude from the gx and gy. So this is the combination of magnitude from gx and gy. So this is in general the final outcome after we perform this type of edge detection process, in which we will highlight most of the important point that was the transition point between the two gradient. So previously I have shown you that if we have just a bit of noise, so your outcome will become much more worse, especially for the second derivative. First derivative will be a bit worse, second derivative will be much more worse. So some of the solution is that we use the what we call as the pre-processing based on the smoothing function prior to applying the edge detectors. So as can be seen from this particular image, we have the same image, and then this is the outcome from our previous operation. We just take the gx, gy, find the magnitude. So this is the total response of magnitude in x and y direction. So without the pre-processing, this is the output. When we implement the pre-processing, we will have some different output. So what is the significant difference when we applying the pre-processing is that, as you can see from here, we highlight most of the distinct edge, more tangible edge, and then the one that is belong to this roof, in which we have some cluttered area, so we don't highlight that thing much after we perform the pre-processing. However, without pre-processing, you see in most of the area, you will highlight in the most of the high cluttered region. So the aim of the edge detection is that we just want to find the most tangible edge from the image, so that this thing can be utilized later on in the higher level processing. In this simulation, I will show you what is the effect of applying the pre-processing or without applying the pre-processing of the smoothing before we applying the edge detection. So basically this software, you can find it in your Google Drive. So let's say we use the second image, the ball G here. So if you can see from this image, we have quite textured image. Which is belong to the ball, and then we just want to highlight the more distinct edge for this particular area. So let's say if we apply the custom filter, so first operation, let's say we apply the smoothing function, and we apply the smoothing much more, and then we applying the edge detection. So this is our resulting image. So second example, if let's say we just highlight in terms of the strength of the contrast of the image, so and then we apply the edge detector. So based on the original image, if you can see from here, so this is the effect if you the almost the same effect if you just applying straight with the edge detectors without any smoothing function. So you can see you highlight the area that belongs to the edge that we want to emphasize. However, most of the textured region here will also be highlighted, and then it will be issued later on. So in this case, we highlight most of the region that we want to highlight, which is belong to the page, and then we can discard or omit the text region. Uh, in order to produce a much more nicer edge detection image. For the second order derivative operator, so you apply the derivative function in x and y direction twice. So this is the continuous function, and then the representation of the continuous function in the digital notation. So the same thing with the first order derivative, in which for the image processing we will be applying the kernel. However, for the second derivative, instead of applying the kernel in x and y direction using the two different kernel, for the second derivative we can actually implement that thing just by using single kernels. Means that you just pass the kernel through the image, and then you can highlight the second derivative order of the edge. However, in order to design this thing, you need to remember that for the second derivative, it can be either the center positive and then the border will be negative, or the center negative and the border will be positive. One thing that you should note is that the total amount of number in the kernel must be belong to 0 in order to ensure that the design kernel will be works properly. So this is the representation of the kernel function for the Laplacian for the 3 by 3 kernel. So, however, as been mentioned previously, for the second order derivative is very sensitive to the noise. Just a little amount of noise can generate much more deteriorated output, or you have very cluttered output. So in this case, as been mentioned previously, it is important that we be incorporated the smoothing operation prior we applying the edge detection. So for the second derivative, we can embed the Gaussian smoothing function inside of the Laplacian operation, and then finally find the edge via the zero crossing by using this notation in terms of the continuous function. So the same representation can be generated by using this type of kernel. So this type of kernel will have the same effect, in which for this kernel the center is positive and then most of the boundary is negative. So the shape of this thing, if you look from top of the image in here, so this is the same effect of the kernel that you will be slide throughout the image. So most of the Laplacian of Gaussian, the dimension will be a bit bigger. So if you reduce the dimension of the Laplacian of Gaussian, so you will have almost the same type of kernel for the Laplacian. This is the example when you applying the combination of the Gaussian smoothing and the Laplacian edge detector. So in the left side of the image, you're applying the Gaussian smoothing function, and then later on the right side of the image, you're applying the Laplacian operator, in which using the 3 by 3 mask. So basically, you can applying the Laplacian of Gaussian in the two ways. The first way is you applying the smoothing and then applying the Laplacian. Means that this is the two pass operation. Or you can design the Laplacian of Gaussian mask as been seen previously, and then something like this, and then just applying this thing to the image in the single pass. So it's up to you to decide that thing, but in a simple way, combination of Laplacian and the Gaussian will generate much more faster response. In contrast, you do the two pass process. In this example, I will show you in a simple way of the calculation how you're able to construct the binary image by using the first derivative operation. So for this type of problem, you are given this type of image in which we have the dimension of 8 times 4 dimension. And then for this image, the first task is that if the threshold value is 200, we need to determine the binary image representation of this thing. So, and then later on, we need to construct the binary image by using the Prewitt kernel. So let's execute the first task in which for this case your kernel will be used this type of operator gx and gy. So for the first process, since the threshold value will be equal to 300, so the binary image for this type of representation is something like this, in which the foreground will be labeled as 1, and then the rest will be background as the rest will be labeled as 0. So once we have highlight the area, so the next task is that we calculate the response of the derivative operation in gx and gy direction. So for the first task, in which we construct the response in terms of the gx direction. So if you noted from this image, so the resultant image dimension will become lower. So in general, the output image when you applying the kernel operation, so the output dimension will be equal to the input dimension minus the kernel dimension plus 1. So this is the you can calculate the dimension of the output as a result of applying this operation. So for instance, for this case, we have the width of the image is 8 and then the height is 6. So using this equation in which your kernel dimension will be 3 by 3. So the output image dimension will be 8 minus 3 plus 1. So in this case is equal to 6 in terms of the width, and then the height of the image is 6 minus dimension of kernel plus 1. So in this case sorry, uh, I think this is supposed to be 4, 8 times 4. So in this case our height will be 4 minus, this is the input, minus 3 is the kernel plus 1. So the output image dimension will become 2. So this is the x response in the x direction. So let me clear the screen first. So the next step, we calculate the response in terms of the same y direction. So how we able to calculate this thing? So for the x direction, we perform the same convolution operation. So let's say this is our kernel, the same kernel of the gx, and then this is the resultant output. So how we able to determine the output is equal to 0? So for this case, you just need to multiply everything here in the left side. So for instance, for this part of the response, let's say the outcome of this thing, 0 minus negative 1 is 0, 0 minus negative 1 is 0, so the same thing here is 0. So this thing will be 0, 0, 0, and then this thing will be 0, 1, 1. In this example, I will show you how you're able to calculate the age when given some digital image. So basically for this problem, you are given this type of image in which the dimension will be 8 times 4. And then the first step is you need to find the threshold, the segmented image when the threshold value is equal to 200, and then second thing is the construct the binary mesh by using the Prewitt kernel. So Prewitt kernel will be given by this operator in which the gx and gy is in the 3 by 3 dimension. So basically, first thing first is since the threshold is equal to 200, so whatever the pixel location that was highlighted here will be become the foreground, and then the rest will become the background. So we can convert that thing into the binary image by using this notation, in which one is the foreground, and then 0 will belongs to the background area. So the next step is that we construct the response of the first derivative in the x and y direction by using this kernel. So how we able to do that thing? So based on the constructed binary image, so the response in the x and y direction is as can be seen in the screen. So basically, one thing that you will notice is that the dimension of the output image, once you apply the kernel, will become smaller. This is general. This is very common because of when you applying the kernel for this type of the image, so you will strike the things in the region of the that can be covered by kernel. So based on this thing, you will start in this location to start the slide process. Basically, the output of the kernel can be calculated by using the simple equation of output of the kernel will be equal to the uh, output of the image will become the is equal to the dimension of the input image minus the kernel dimension plus 1. So for this case, dimension of the input is 8, and then 8 times 4, and then for the output dimension of the width is 8 minus the kernel will be 3 plus 1. So the dimension of the output will equal to 6. And as for the height, the same thing. The input dimension is 4 minus the kernel plus 1. So you have the dimension of the output is equal to 2. So this is the way you're able to calculate the output response dimension as a result of applying different type of the kernel shape. So let's clear up the screen first. So now you know how to calculate the output dimension. So now how we able to calculate the value response for each of the x and y direction. So for this case, you put the first derivative operator of the gx in here. So for this location, the output is equal to 2. So how we able to calculate number of 2 is based on the performing the convolution operation for every items inside of the kernel. So for this type of the kernel, so the output for this part is 0. This thing is equal to 0. 0. 0 times negative 1 equal to 0, the same thing for every 3 items. So for this case, 0 times 0 is 0. So this is 0, and then this is the same thing 0, 0, 1, 1. So you sum up everything. So that is because you have this number of 2. So let's try to calculate that thing in the next part. So we are in the second location. So for this second location, the output for the gx is equal to 3. So for this case, the same thing. For this part is, so this part is 0, the output 0, 0, and then this thing the same thing 0, 0, 0, and this part 1, 1, 1. So sum of everything will be equal to 3. So clear everything. So we move on to the third location. So for the third location, the same thing. Everything here is 0. Everything here is 0. So you sum everything here will be equal to 3. Fourth location, everything here is 0. 0, this is 1, 2, 3, so the outcome is equal to 3. The fifth location, so for the fifth location, this is 0, 0, this thing will become negative 1. Everything here is 0, so 1, 2, so 2 minus 1 will be equal to 1. And then for the final location, this is 0, negative 1, 0, 0, 0, 0, 0, 0, 1. So 1 minus 1 will be equal to 0. So the same process will be repeated for the second location here. So finally, you have the output image calculated for the first operation. Sorry, for the first operator in the gradient of the x direction. So the next part, the same thing will be happening for the y direction for the gy gradient calculation. So only for this case, we will have a different type of kernel. So in this case, for our kernel here, let's say for the first location, so this is belong to the first location. So for the first location, the same thing, everything here is equal to 0. Everything here is equal to 0. So this is 1, 2. So you have the output of 2. So we will repeat the whole process, the same thing, until you get the output response that correspond to the GY. So we have calculated the gradient in terms of the GX direction and then GY direction. So the next part is we need to find the whole magnitude from the GX and GY. So this can be easily done by using this simple approximation in which you find the absolute value of x and absolute value of y. Absolutes means that for every value here, if the value is negative, it will become positive, and then you just need to sum up gx and gy straight away. So in this case, if you sum up gx and gy straight away, you can obtain this value. So let's say for this case, 4 here is actually 2 plus 2, so you have 4. So let's say I pick up some value here, so 1 here is 0 plus absolute value of negative 1, which is equal to 1, so you have the value of 1. So it can be simply calculated by using simple addition operation. So finally, once you have calculated the whole gradient magnitude, so the final part is to determine which location that will become edge or edgel. So in this case, it will depends on the threshold value. But for this case, we just simply put that every value that is not 0 is actually the edge or the edgel. So for this case, whatever location that we have the value that is not 0 will be marked as 1, and then 0 will be belongs to the area that belongs to the edgel. So this is the whole process. It's quite simple, and then it's quite straightforward. Only you should note that this is the most important thing, in which you need to find the response in x and y direction, gx and gy. So this is the first step. And then I think the second and then the final step is very straightforward, and is quite simple to calculate. So finally, let's recap on what we have done so far. So for this case, you have the input image of the grayscale. So the first step is to calculate the segmented output by using the threshold equal to 200, and then using the Prewitt edge detectors, with will be corresponding of the output calculated for this type of kernel, gx and gy. You just need to implement the gx calculation, magnitude of x, magnitude of I, and then the whole magnitude, and then finally find the threshold before you mark the area that belongs to the edge or not by using outcome calculated from the total magnitude. So once we have determined the age, so the next part is how we're able to link between all the age location. So basically, let's say this is the agile location of the square object in which you have calculated previously. So the next part is how we're able to link that thing together. So if you still remember, so for every first gradient operator, we calculate the magnitude and we can calculate the direction. So let's say in the first derivative operation, we calculate the gx and then we calculate the gy. So the magnitude can be calculated easily by using the gx squared plus gy squared, the square root of this thing, or you can simply use the absolute value of gx and gy. However, for the direction, if you have the x and y value, you can determine the direction by using the antitan of y over x. So you can determine the direction for every edge by using this notation. So magnitude and the direction for the angle. So we can utilize this information in order to determine in which of the edge or the edge we have the similar magnitude and the direction so that it can be linked together. So for instance, let's say if I pick up some point in here, there is some tendency that your direction calculated will be in a simple, so in a same direction. So we can mark this area belong to the same edge, and then we can link that thing together. So the same thing in here. So we can, if we pick up the actual location in the first point and then the second point, so there is some tendency that the direction calculated for the same line here will belong will be the same, and then we can link the thing straight away together in the same properties of direction and the magnitude. So this is the first step in order to link the edge, which is based on the local processing method. uh, the second method, okay, before that, so this is the example of how we're able to implement the edge linking by using the local method. So the grayscale image, you find the response x and y, and then finally we can get the magnitude direction by combining information from the magnitude and the angle before we can link that thing together. So the second method of the edge linking is based on the global method, which is known as the Hough transform. Hough transform is a very useful method in order to determine straight line, circle, and etc. Is widely used in most of the application, and because of that, I will explain more details about how we're able to use the Hough transform in order to link between agile. So for the half transform is a matter of we calculate the input from two different plane. So let's say in general, let's say we have the three edge or edges here, 3 point of edge, which is in the three different line, black, green, and blue. So for this type of the axis, we mark a y and x. So in general, most of the equation of line from here we can determine by using y equal to mx plus c, in which m is the gradient, and then gradient of the line, and then c is the intersection in the y-axis. So this is straightforward in terms of the calculation in the Cartesian space. So for the half transform all the inputs in the Cartesian space into the half space. So half space, in simply put, is that for this Cartesian space, y m and c is the constant and y and x is the variable. So for the half space, you just need to rearrange a bit this equation, in which for this case c equal to negative mx plus y. So we change the plot, in which for this case c and m is the variable, because we put the thing here in the axis, and x and y is the constant for this case. So if we transform that thing from Cartesian space to the half space, so what will happen is that the concept is that for every point in Cartesian space, when you transform the point in the half space, it will generate a line. And then for every line constructed in the half space, if you transform that thing into the Cartesian space, it will become a point. So the same thing will be happening. If you have line in Cartesian space, you transform to the half space, it will just become a single point. So I will show you the illustration. So let's say for this part, we transform the point to the half space. So this is the point, and then we generate a line in the half space. So the same thing for the second edge, for the green part. So it will generate another line in the half space, and then the third point will also generate the third line in the half space. So in the half space, what we need to find is that we find in any location where every line will be overlap or intersect between each other. So if you have many lines, you need to be fine in the Cartesian space. So there is some tendency that you will have many lines that intersect in the half space. But for this case, for simply to explain, for simple explanation, we just assume that we just need to find a single line in the Cartesian space. So we have three lines generated. So this is the intersection point. So we mark the intersection point. So for this intersection point, we can straightway determine the C, the intersection, and M. This is the intersection point in half space, and this intersection point will become, I label it as the C prime and then M prime. C prime is the intersection in the half space, and then M prime is the intersection in the x direction of the half space. So if you still remember that C and M in the Cartesian space is actually belong to the magnitude, and then this is the intersection in the y-axis. So we take this point, the red point, and then we plot it back into the Cartesian space, so we can find the line that is the estimated line in which you combine the three edges here. So by using this equation of line, you can link together these three dots of edge in Cartesian space by using the half transform method. So the idea is quite simple. Means that you in every edge, you transform the edge into the half space, it will generate line. So in the half space, you analyze in the half space where is the location, the most intersection of line happening. Then you take that point and then transform that point back to the Cartesian space in order to generate a line that is in which the line will be linked all the edges or most of the dominant edges in the Cartesian space. So basically this is the concept of the half transform. So you can use this equation simply because M, we pick up the thing from the intersection point here, M prime, C prime. You pick up that thing here, and then you can plot the line straight away. So this is some of the example how we are able to link the line in the half space. We have the image here. We can segment the image. We have the edge, and then from the edge we can estimate the intersection point, the most intersection point. This is using the polar coordinate, we'll show you later on. And then for the every intersect point here, the high accumulation of the intersection point, we plot it back in order to generate line in the Cartesian space. So this is one of the example of the extension for the Hough transform, in which instead of the finding line, for this case we find how many circles that can be drawn based on the based on the cell generated from this image. So in this case, if you're able to estimate how many circles that can be overlapped in every of the image here, we can calculate how many red blood cell, how many white blood cell that appear under the clump condition or highly overlapping condition. So you have known in general the concept of the Hough space, Hough transform, in which a Cartesian to the Hough space find the intersection line and then apply it back in the Cartesian space so that you have the single line. So this is a more detailed explanation on how we're able to use the Hough transform. So in this case, we will use a bit different notation to give the equation of line, in which for this case y equal to kx plus m, in which k is the gradient and then m is the intersection in the y-axis. Almost the same thing with the previous one, only we change the variable name. So for this particular case, we can estimate this shape is the triangle if we're able to determine the three different equation of line. So we have three different equation of line, so we can assume that this object is triangle. 4 means that we have either rectangle or square, so this is quite useful in order to estimate or predict what type of image that was fed to the system. So for this case, let's say we use the same notation previously, in which y equal to kx plus m is the intersection, then k is the gradient calculation. So you are given 4 points in this case, 1, 2, 3, 4, 4 points, in which the coordinate is 3, 1, 2, 2, 0, 4, and 3, 4. So the first step is we plot this thing into the Hough space. We can plot this thing into the Hough space by using simple rearrangement of this equation. So we have m equal to negative kx plus y. We just need to put this thing in here. So our original equation is y equal to kx plus m. So if we change a bit, it will become m equal to negative kx plus y. Okay, so now for every given value here, what you need to do is that you can just straightway plug in the value in order to determine the equation of line. So for this case, for the first one, m1 equal to negative k plus 3. So y equal to 3 here, and then x equal to equal to 1. So you have the equation of line for the first point is m equal to negative k plus 3. So for the second point, x equal to 2, y equal to 2. So we just put it here. So you have m2 equal to negative 2k plus 2. Third line, m3 equal to negative 4k plus 0, because you don't have any intersection. Your point of y equal to 0. And then finally, the last point, the equation of line equal to m4 equal to negative 4k plus 3. You just simply plug in all the value of x and y in this modified equation so that you determine equation of line. So for this case, you have 4 equation of line. We have the 4 equation of line in Hough space. So next we plot all this line into the Hough space. So this is the equation that we have calculated, 1, 2, 3, 4, and then we plot this equation of line to the Hough space. So this is all the 4 line. So you can see from here the line of m1, m2, and M4. M1, M2, M4 intersect between each other, whereas the M3 does not intersect with respect to the any line. It will intersect with M1 and M2, but only in the one intersection point. Compared to this thing, this is the high density of the intersection point. So we will pick up this point, which is the high density of intersection between each of the line. So this is we assume as the outlier. Outlier means that it does not belong to the most of the dominants in the intersection point. So for this case, if we mark this area, so the value for this intersection is m equal to 4 and then k equal to negative 1. So this is the approximate location of this thing. So if we utilize back this thing, so we have the m equal to 4 and then k equal to negative 1. So if you still remember, we have the equation y equal to kx plus m, which is our line equation in the Cartesian space. So we just need to plug in this information back to this equation. So m equal to 4, here is 4, you have 4 here, and then k equal to negative 1, just plug in here. You have the equation of line y equal to negative x plus 4. So this is the more detailed explanation on how you're able to construct the line in half space and then find the intersection point, and then finally reconstruct back the line in the Cartesian space. They're able to uh, connecting between every edge. So you can see from here, these three lines can be connected between each other, whereas the other line, the other point here, this is the point here will actually belong to this line. So this is that we call as the outlier for this particular case. So one of the biggest issues, if we use the Cartesian coordinate in order to construct the half transform in the half space, the biggest issue is for this case instead for the vertical line, because of for the vertical line, your gradient is equal to infinity. So let's say for this case, if you have the y-x, so usually if you have this line, so this is the gradient calculation. So the gradient calculation will be equal to y over x in general. But for the straight line here, something like this. So for this straight line, so y is actually equal to infinity, and then x will be x prime. So this is the issue because of if we stick to the Cartesian space uh, conversion, so we're able to handle any issue related to the straight line. So there is some improvement for this method. How we able to solve this thing by using the another conversion, which is we call that thing as the polar coordinate conversion. So previously we converted thing using the gradient and intersection. For the polar coordinate, so we calculate in terms of the r and theta. So what is r and what is theta? So I will show you in the illustration below. So we use the same example. So in the Cartesian space, we have the three edges. So we want to find what is the intersection line for this problem by using the half space using the polar coordinate conversion. So polar coordinates, the step is that you need to for every edge, you need to construct the line, approximate of line in different angle. So for this case, we construct the line in 0, 45, 90, 135. So usually it will be done in the higher resolution, which is 0, 1 degree, 2 degree, and etc. in order to determine exact location. But for simplicity, I will show you in 45 degree resolution. So first we construct the equation. Sorry, we construct the line in every angle from the each location. So once we have constructing, the next part you need to remember we want to find for every location a set of, let's say this is the, I mark this thing as the agile one. So for the agile one, we want to find a series of theta and r. So for this case, your theta is 0, 45, 90, 135, and then you need to find the set of r for the first agile. So the same thing will happening for agile 2. If I mark this thing as the agile 2, and then the final, the blue spot is the agile 3. So for the agile 2, the same thing. You find the set of theta and r, the same resolution, 0, 45, 90, 135. So all the three agile theta are 0, 45, 90, 135. So the issue of how able to find the r. So r is actually calculated from the origin, from this origin here, to the perpendicular with respect to the angle. So let's say for the zero angle, so your r will be calculated from this particular distance. So for instance, this is for 0. For 45, we construct straight line and then find the perpendicular direct magnitude. So this is the magnitude of r for 45, and then for 135, something like this, the same thing. And then for, sorry, this is 90, so 135. So this is actually three different type of calculation. How we able to determine the r based on the given every angle of 0, 35, 135, 90. So we calculate series of this thing. So let's say this is the R0, this is R45, R90, and then R135. So you have calculate everything. But you need to remember we have to calculate the value of the set in between of every agile that you can found in the Cartesian space. So we calculate the value for every r and theta, a set value of theta and r for every agile. So once we able to find that thing, so the next part is that we find the similarity. So in this case, if you look at the things in a simple word, you can see that. Let me clear the screen first. Okay, for this case, we want to find in which direction that r is the consistent. So for this case, if you look at every line here in 45 degrees, so in 45 degrees, for every 45 degrees, you can calculate almost consistent value of r for every agile 1, agile 2, and agile 3 location. Let's say if you pick up 0, 0 degree. So for the 0 degree, so this is the calculation of agile 0 degree for the first agile. So for the second agile, you see, it will be a bit longer, and then for the third edge it will be the same thing, right? It will be much more longer compared to the edge number 2. So it's not consistent, the r calculated is not consistent for the zero angle. So for the 45 angle, so since this is 45 degrees, so most of the calculation of the r will be consistent. So for this case, we pick up most of the consistent value of the r for every agile location. So in this case, let's say we predict that we pick up the optimal consistent value of r is based on the 45 degrees, so we just need to pick up the r45 value, which is the length from origin to the perpendicular of the 45-degree angle. So we have the r and then we pick up the angle. So what we need to do next in order to find the line, so we just need to put that thing in this particular equation, in which r45 is our calculated magnitude from the origin, and then we just need to plug in the 45 degree of the angle, in which this is a consistent angle for the value of r. So we just need to plug in everything here, and then eventually you can determine y equal to mx plus c by rearrange back this equation a bit. So this is how we use the Hough transform in the polar coordinate space in order to determine the output value. So basically this is the summary of how we're able to calculate the Hough transform, in which this is the general equation. You have the d here is equal to r, the same thing. This is the magnitude from origin to the perpendicular of the angle of line. So theta is the angle of resolution for every edges. So this is the whole step of the algorithm, how we're able to find the most intersect point of the Hough space in the Cartesian coordinate representation. So this is another example. The example will taken from the Wikipedia. You can find the example in the Wikipedia. I just want to show you some simple example of the calculated output. So let's say you have, in this case, we have three edges: first edge, second edge, third edge. So this is the series of the output calculated for the edge 1. This is edge 2. This is edge 3. So if I label the things properly, this will be edge 1, edge 2, and then edge 3. So we do the same, we repeat the same process, only this thing in the 30 degrees resolution of angle. So the most important thing is that how we hypothesis the output in order to determine the consistent value of the distance for this case. So let's say for zero angle, you see the distance calculated was 40, 57, and 74.6. So it can be clearly hypothesized that this is not the location of the straight line. Next, we move on to the 30 degrees. 30 degrees, first distance 69, second 79, third 89. So it can be clearly conclude that this is not belongs to the line. So the third one is 81, 80.5, 80.6 is quite consistent. So we just mark the thing first. So for the 90 degree, 70, 60, 50, so it's not consistent. And then for the 120 degree, 40.6 to 23, 6.0, so it's quite clearly seen that this is not the right magnitude, not consistent. And then finally for the 150 degree, 0.4, negative 19.5, negative 36.39.6. So the most consistent magnitude is based on the 80 degree. So for this case, we can say that 60 degree produce the consistent distance. So how we able to determine the magnitude? We can find the average of the magnitude from this case, 80.6 plus 80.5 plus 81.2 over 3. So if this particular equation was illustrated, so this is the sample plot of the three different edge location calculated for every angle. So this case is angle 0, 30 degree, 60, 90, 120, 150. So you can see from here, so this is the most consistent line, most consistent magnetic calculation. Most consistent means that this is the area where the curve of the polar coordinate equation was actually intersect between each other. So we choose this thing in order to construct our equation of line in the Cartesian space. So this is some simple illustration how the things work in order to determine the intersection point. So we have first angle here. So we have the series of the constructed curve in different angle from 0 to 180. So we have the second angle here. So you can see from here for the second angle was actually intersect in here. So in this case, we can pick up the magnitude of r here, magnitude of r and theta in the location where uh, both line intersect between each other. So we can use this thing in order to estimate the straight line uh, in the Cartesian space. So some extension of the Hough transform means that we can use this simple concept in order to compute the maximum density of intersection, and then we can extend this thing for circle, square, and any of shape detection. So we have back let's recap back on what we have learned so far for the segmentation. So this is the first example in which you use the threshold in order to determine or to separate the foreground from the background. So most of the analysis can be done by looking at the histogram of the image, in which whether you can decide whether we should use the global or the local method in order to threshold this image based on the distribution of the histogram. And then finally, we based on the constructed binary image as a result of the segmentation process from the thresholding, you can find the edge location, and then you can link that thing either by using the local method or the adaptive method. For the edge detection, you have two type of the operators, for the first gradient and then the second gradient. So that's the thing that recap on in the segmentation section. So later on, we will move on to the third part of the chapter, in which how we're able to analyze the image in terms of its contrast, its illumination, and etc. Thank you.